Here we're going to learn about linearizing equations. We're going to start with the simple equation, our old favorite equation, the Rayleigh-Benard temperature or buoyancy equation. This is the time evolution of temperature with advection of temperature and diffusion of temperature. So this is the fully nonlinear equation. And to start out, we're going to first introduce a decomposition. This is the first step in actually linearizing the equations. And we have not yet actually made any assumptions when we do this. We're just rewriting the equation in a convenient form. So what we're going to do is we're going to take the temperature T, and we're going to define the temperature T to be two parts, a T0 and a T1. And right now, as I said, we haven't said anything about the sizes of T0 and T1 relative to each other. We haven't thrown away any terms. Now this temperature here, this T, this is a function of space, of all the possible spots in space, and also of time. We'll find it very convenient if we decompose things into a part that is simple in some sort of way. So this T0 here, we're going to make this a function of maybe one coordinate only and not of time. So here I've written it as T0 of z. We're going to think of this as like a non-constant coefficient in our system. Non-constant coefficient, something that's part of our system, our atmosphere, our background. And our T1 here, this is some sort of fluctuation around that. It's some function of all positions in space. It also can evolve in time. And we haven't said anything about its relative magnitude to T0 yet. Sometimes this is written, this is sometimes also written as T prime. I will use the T1 and T0 notation. I find the T prime notation to get confusing, especially as we start talking about derivatives later on. Okay, so now let's take our system here and let's rewrite our temperature equation in terms of this decomposition. So I'm going to write, all I'm going to do is I'm going to introduce this decomposition into the equation, d by dt of t, so that's d by dt of t0 plus t1 plus u dot grad, this is our advective term here, and this acts on both T0 and on T1. And this is equal to our thermal diffusion part, chi del squared, our Laplacian operator, on both T0 and T1. All right, so all we've done is rewrite our equation. We haven't said anything new and different. Now we can simplify things a little bit. We can see that in this equation, since T0 has no time dependence, this part is going to be 0. There's no time dependence of T0 by the definition we made. There are gradients of T0, so the gradient term still remains. And there could in potential be a Laplacian of T0, so that term also remains. But the way we define T0, there's no time derivative to it. Okay. So I'm going to take this equation and I'm going to rewrite it again. I'm just going to gather terms in a convenient way. So I'm going to write d by dt of t1 plus u dot grad on t0, and let's decorate our vectors here. And then we're going to have a minus chi del squared t1. And I'm going to take the other terms and move them on the right-hand side. So we have a minus u dot grad T1, and we have a plus chi Laplacian on T0. I've written this in a special form. All these terms here on the left-hand side of the equation, these are terms that are linear in our variables. So what do I mean by our variables? I mean u and our fluctuating T1. These are the things that depend on both on position and on time in our system. And these terms are all linear. So the time derivative, it has one appearance of a variable. Our advection term, it has one appearance of a variable, and our Laplacian term has one appearance of a variable. Now these terms on the right-hand side, these are not linear. In U and T1. The advection term is nonlinear. It has two occurrences of U and T1. We call that a quadratic nonlinearity. But this term is also not linear. This chi del squared T naught is not linear because neither T1 nor U appear in it. It's just some constant in time heating term within our system. Now this approach that we've been doing so far, this is completely general. We haven't said anything about amplitudes or anything else. And so this is just a decomposition. This is completely general. Completely general. So we've just redefined our problem. We haven't said anything so far. Now we're going to move on to the process of linearization. And in linearization, we're now going to make some assumptions that are going to break the generality. Okay, so what are we going to do when we linearize things? So what we're going to say is we're going to say let our solution variables u and t1, let them have some sort of amplitude. Let them be order epsilon. And let epsilon be some small number, very much less than 1. Okay, so now looking at our terms, we have things that are the size of our solution variables, t1 and u, and Laplacian of t1. These are all the same sort of size as our solution variables. And we have other terms that are not linear in our solution variables that either don't have them at all, like the heating term, or that have two occurrences of them, like the advection term here. All right, so now we're going to come down and consider the relative amplitudes of these different terms. So I'm going to write our equation out again. We have d by dt of t1. We have plus u dot grad on t naught. We have our diffusion term, chi del squared t1, and we have this equal to minus u dot grad t1, and we have a plus chi del squared t0, our constant heating term. So as we consider these terms here, we can see that each of these has one occurrence of a solution variable, And so all of these terms are the size of a single solution variable. These are order epsilon. This has two occurrences of a solution variable. It's quadratic in the variables of our system. So this is an order epsilon squared term. And then this has no solution variables at all. And so we might call this an order 1 term. It doesn't have any of the small variables in our system. All right, so in classic perturbation analysis, what we would do now is we would grab our different ordered terms and write out our order equations. So let me do this for you now. So in this, we'll start with big. We'll have our order 1 equation, and our order 1 equation is that chi del squared t0. There's our order 1 term. There are no other order 1 terms in the system, so chi del squared t0 is equal to 0. This, by the way, immediately tells us that t0 of z is some linear function a plus bz, some linear function of z, because there is no second derivative of it. The second derivative, del squared of t0, is equal to 0. So that is what we would call our equilibrium solution that we might be studying dynamics around. All right, let's now write up our order epsilon system, our order epsilon system is that d by dt of t1 plus u dot grad on t naught minus chi del squared on t1 is equal to 0. And then we have our order epsilon squared system. What are our epsilon squared fluctuations? Our order epsilon squared fluctuations are that u dot grad t1, these are the only order epsilon squared terms in the system, and these are order epsilon squared. And since epsilon is already tiny, this is considered to be 0. These terms are 0, and there's nothing to balance them. This leads us to the linear equations, the linear equations, which we can also think of as our order epsilon perturbation equations, which are that d by dt of t1 plus u dot grad t0 minus chi del squared t1 equals 0. So now we've taken our temperature equation and we have linearized it for small perturbations t1 and u around a background. Now, the system that we've studied so far is just one equation. We have one equation here, and we don't have an evolution equation for u as well. We would need that to actually solve this system. If u was some prescribed flow, if u here was a prescribed flow, then this would be a non-linear term. It's not linear in our variables. So if u is a prescribed flow, then we'd have a slightly different system. If u is not an evolving variable of the system, then we'd have an order 1 balance that had that chi del squared t0 plus or minus u dot grad t0, so collecting those terms on the same side, is 0, and we'd have an order epsilon perturbation system. And that order epsilon perturbation system is a little different now. It's d by dt of t1, so that remains the same. But now we have a u dot grad t1, because u is now some order 1 quantity potentially, and then minus the diffusion chi del squared t1 equals 0. Lastly, if u equals 0, then we get the classic heat equation, d by dt of t1 minus chi del squared t1 equals 0. Heat equation. In our next lecture, we'll learn what to do when we have a system of equations, including, for example, u as well as t1.